Hello, everybody. In this lecture, I'm going to talk about Coulomb's law, which is the subject of chapter 21, section 1. And for this lecture, I'm going to talk about it in kind of general terms and give the basic idea. In the next lecture, I will do a couple of example problems. So for this lecture, Coulomb's law refers to the force between two electric charges. It's very similar in some ways to the gravitational force between two masses that I talked about in the previous two lectures. A couple differences though. Coulomb's law, the force between two electric charges can be not only attractive, but repulsive. So we'll see that. It is an inverse square law, and we'll see that its mathematical form is very similar to the gravitational law, Newton's law of universal gravitation, but it's also much stronger, a very much stronger force. And so a question you might have is, why do we not usually experience this electrostatic Coulomb's force? It's because there are positive and negative charges, and these attractive and repulsive forces between these charges tend to kind of all balance out, unless you take some of the negative charge and move it away from the positive charge and make things imbalanced. But let's go ahead and look at the mathematical form and some aspects of Coulomb's law here. So I'm going to share my notepad here. Hopefully you can see that okay. So again, Coulomb's law, chapter 21, section 1 of the textbook, and that's both textbooks, Halliday and Resnick, and the OpenStax textbook. So first of all, recall gravitation for a moment. Newton's law of universal gravitation, the force between two masses. So I would kind of speak of the masses as being the source or the cause of the force, right? Any two masses, you get this force acting between them. And this force is always attractive, and it has a very small proportionality constant, 10 to the negative 11. It's very tiny. So it's actually a very weak force, and you need a lot of mass to add up to even a slightly strong attractive force. All right, so let's go to Coulomb's law, the electrostatic force between two charges. So first of all, let's talk about electric charge. I usually denote it with the letter Q, and the units in the metric system are coulombs, which we'll usually denote by a capital C. Now the unit, a charge is actually very tiny in coulombs. Usually you have a very small amount of charge. And in fact, there's a smallest or fundamental amount of charge in the universe. And it's the charge on an electron or a proton. As it turns out, the electron is negatively charged and the proton is positively charged. But they have the same amount of charge in coulombs, 1.6 times 10 to the negative 19 coulombs. And sometimes you will see this quantity denoted by the letter E, 1.6 times 10 to the negative 19 coulombs. And so that amount of charge is the fundamental amount of charge that you can have. It's the smallest. And I say that charge is quantized, which means that if you had a certain amount of charge bigger than this fundamental amount, it would be a multiple of that 1.6 times 10 to the negative 19 coulombs, right? And so what would happen is you'd have 3 or 4 or 5 E amount of charge, maybe up to millions of that amount. But every charge in the universe is a multiple of this fundamental amount of charge. So let's say I have two charges, Q1 and Q2, and I put them close together. All right, well, again, we're talking about a force, and forces are vectors. So we need to talk about the direction and the magnitude. So again, for Coulomb's force, electrostatic forces, you can either have attraction or repulsion. The rule for direction is opposite charges attract, like charges repel. Right? So if I bring up two positive charges close to one another, they will push apart. Again, Newton's third law must still apply. So this charge will push with a force this way on this charge, and the other charge pushes back with an equal and opposite force. Now, if I have a negative and a positive charge, opposite charges, they will attract one another. Right? Again, two negative like charges will also repel. So that is the rule we'll always use to get the direction of the force between two electric charges. Now, what about the magnitude? Right, so the magnitude, again, gives me the number of the force in newtons between these two charges, Q1 and Q2. If you look at it, it looks very, very similar to Newton's law of universal gravitation. I just have charges instead of masses, and I have another constant, K, a different proportionality constant. But it is an inverse square law, just like we talked about for gravitation. All right, so what is this K? It turns out it is a very large number, 9 times 10 to the 9 Newton meters squared per Coulomb squared. And this means that electrostatics or electrical forces are very much stronger than gravitational forces, right? And of course, since we have positive and negative charges, they all kind of balance out. There's repulsion and attraction going on at the same time. So you don't usually notice this electrostatic force, whereas gravity is only attractive. And so you notice that gravitational attraction from the Earth, which causes your weight. But as it turns out, if you can separate positive from negative charges, electrostatic forces will dominate. But you have to separate those charges in one way or another. And maybe I'll talk about one example of that here in a moment. But let's talk a little bit about where we find charges. Right? For example, the atom. Nowadays, we know that the atom consists of fundamental particles called electrons, protons, and neutral particles called neutrons. Back in the days when people were first studying this, and Coulomb actually did his experiments in, I think, the late 1700s, people did not even know atoms existed. So there were many different theories of what was going on. Right? And in fact, I think it was Benjamin Franklin who came up with the designating negative and positive charges. But again, all of this force law was found by doing experiments, right? Putting two charges together and seeing what force they repelled or attracted with. But for the atom, we now know, right, the protons exist in the nucleus, and protons are very heavy. Proton mass, I mean, of course, compared to normal things, it's not, but it's 1.67 times 10 to the negative 27 kilograms. Whereas the electron mass is much smaller than that. It's only 9.1 times 10 to the negative 31 kilograms. Right, so the proton mass is about 1,800 times the electron mass. Since it has so much mass, right, you can't move it or accelerate it as easily as you can these electrons. And that's why we usually think of the nuclei, the protons in here, being pretty much stationary, whereas the electrons are flying around, orbiting, right, the nucleus. And so the electrons are much lighter, but they do have the same amount of charge, right? 1.6 times 10 to the negative 19 coulombs, as the protons do. They're just negative instead of positive. So a couple other aspects, just real quick, of Coulomb's law. The electrostatic force is responsible for holding all molecules together, right? And so you can have a couple cases. You can have what's called a covalent bond, where there's a buildup of the negative electron charge in between, right? And because of this negative charge, it attracts both of these positive nuclei. For example, in a diatomic molecule like H2 or nitrogen N2. And so that little buildup of charge in between causes that attraction that holds the molecule together. Now, another type of bond that you can see is, for example, sodium chloride salt. The chlorine likes to take an extra electron from the sodium, and then you've got a positive and a negative opposite charge attraction. We call this an ionic bond between them. On a more macro scale, you can see effects of this actually electrons kind of moving in the molecules. If you've ever taken a balloon and rubbed it on your head, right? If you rub the balloon on your head, you might notice as you pull it away, right, your hair tends to stand up. Well, that's because the balloon has taken electrons from your hair and left your hair positively charged. The positive charges in your hair want to repel each other, and so that makes your strands of hair actually stick up. The balloon has taken those electrons, so it becomes negatively charged. Right? Now, what if you bring that balloon up to a wall? You may have done this before and noticed that you can actually make the balloon stick to the wall. What's happening here? Well, the negative charge in the balloon is going to push those electrons in the molecules in the wall a little bit away, right? They can't get completely away from the nucleus, but they'll try to get as far away from the like charges in the balloon. Now, the protons can't move very far. They're stuck in place pretty much because they're so heavy. And they are now closer to the negative charge in the balloon. The attractive force from those protons, since they're closer, is bigger than the repulsive force from these electrons, since they are further away. And the balloon will actually stick to the wall. And we call this polarization. We're polarizing, moving the negative charge of the molecule from one side to the other. It's interesting, though, this shows how much stronger the electrostatic force is than gravity, right? Just by rubbing that balloon on my hair, I have been able to stick it on the wall and cancel out, basically, or overcome the weight, the gravitational force of the entire mass of the Earth, right? The weight is not strong enough to pull it down anymore. That electrostatic force, just from that little bit of charge, easily overcomes the entire weight or entire gravitation of the Earth, right? 5 times 10 to the 24th kilograms, that huge mass. Just one other aspect really of electric charge. Charge is conserved. By conservation of charge, I mean that you can't lose positive or negative charge. The total charge in the universe has to add up to zero, right? If I consider positive charge positive, negative charge negative, the sum must stay zero. So I have the same number of positive charges as negative charges. A couple of things that can happen that are kind of maybe a little beyond the level of this class at this point, but I'll mention. We can have something called electron-positron annihilation. There exists a particle called a positron that has the same mass as the electron, it just has a positive charge. Turns out if you bring these two together, they disappear. Well, they don't really disappear, they turn into light, and in fact, photons of light, particles of light. If you've ever heard of a PET scan, positron emission tomography, this is the process that goes on inside your brain, for example, that emits the light that is detected by the PET scanner. But since photons don't have any charge, this is an example of conservation of charge, right? The total amount of charge in the universe is zero. You could do the opposite of this. You could do what's called pair production. Turns out you could have two photons hitting each other and spontaneously producing a positron and an electron, right? But again, net charge is zero. If you've taken chemistry, you may have seen this conservation of charge. Whenever you look at a chemical reaction, the amount of positive charge and negative charge on each side must remain the same. Okay, so that's basically what I wanted to say about electric charge and Coulomb's law at this point. The next video, I'll do a couple of examples actually applying Coulomb's law to calculate the force between two or more charges. So we will see you in that video here soon.